Good evening. It's a pleasure to be here. As Taft just related, I usually come here for work. I've been here now 25 to 30 times. This does feel like home away from home. But I've never had a chance to speak to people here. And because of the lights, I can't see you all very well. But hopefully this comes across as a very interesting talk. In January of this year, we have a group called the SBAG, which is a Small Bodies Advisory Group. It's a group of cometary and asteroidal and Kuiper belt and Trojan asteroid scientists that get together and try to figure out what we're going to do next in terms of NASA missions and what we're going to study in the solar system, and we advocate for that. And at the January meeting, Dr. Lindley Johnson, one of the NASA headquarters leaders of the solar system programs, asked for a volunteer to help with the Comet ISON campaign. And when I heard this, I kind of had a little thrill inside me, and I kind of stood up and said, I'd be willing to do it. And nobody else did. Nobody else wanted the job. And the reason I volunteered was because I'd been coming out here for years looking at comets, so I knew most of the comet community. I work with Taft and with the IRTF director to help oversee the NASA time that's spent on those telescopes, so I knew the telescope community. And I knew the headquarters folks, so it seemed to me like I was just going to be talking to my friends every day. Well, over the last 7 or 8 months, it's pretty much talking to a number of my friends every day. We're like 5 or 6 or 7 emails a day. This comet has not stopped getting a lot of attention. Tonight I'll tell you why I think it's an interesting comet, but I also want to explain to you why it's not the comet of the century for simple, beautiful, bright cometness. It's not going to be Hale, Bopp in your skies. On the other hand, it's going to be a fantastic comet that's coming from the very beginning of the solar system, and it's going to go right on top of the sun, something that happens maybe every 40 or 50 years. For that reason, it is the comet of maybe the half century. So without further ado, let me explain to you a little bit of background about why comets are interesting, why we study them, other than the fact that maybe we're just obsessive about these things, and explain to you why it's been a wonderful career studying these objects. So what you see here are 3 objects. These are 3 comets that we have come by closely. On the left is Comet Ville 2. That was the target of the Stardust mission. That was the mission that actually brought back little pieces of dust from a comet. And the numbers you see there are in kilometers. So that's roughly, if you will, that body is roughly melon-shaped, or think of watermelon-shaped. It's kind of roundish. It's got all kinds of little pits and depressions all over it. The number PV you see below that is telling you how, it's what we call the geometric albedo. Basically, it's 0.04, 0.03, 0.05%. These bodies, even though you can see them up here, have all been computer processed. I want you to think they're all darker and blacker than the tar in asphalt in your parking lot. They're darker than coal. These are some of the blackest, or probably the blackest bodies in the solar system. We think most likely it's a combination of a mixture of organics and carbonaceous soot-like material, but also they've been burned by UV and cosmic rays for many, many millions and billions of years. So while we process them, oh no, don't do this. Please don't do this. No! That is my computer going to sleep. Here's hoping I can bring the PowerPoint back. Okay, so while we're bringing the PowerPoint back, hallelujah. It doesn't always do that. In the middle is Temple 1. This is the target of the Deep Impact mission. I was lucky enough to be on that. And we launched in January 2005, and just 6 months later, we got run over by the comet. That's our official position. We didn't hit it. We got in the way and it ran us over. And we hit it. Oh, I got a laser pointer here, or it's actually kind of fun to go up on the screen because I like walking on the stage. We hit it between these 2 craters. And we hit there, and it was the equivalent of shooting a bullet from Beijing and another one from Washington, D.C., and having them hit. We hit it 10 kilometers, 6 miles a second. And we hit it with something about the size of, we typically say, trash compactor and ottoman. For some reason, furniture analogies always come to mind. So, and we hit it with more energy than if that 350, 360 kilograms of little impactor spacecraft was made out of even nuclear material. An incredible amount of energy. And we put just a tiny little hole in it. When you look at this object, I want you to think of a body, I was doing the math, it's about the size of Mauna Kea. Okay? It weighs a lot less. Mauna Kea's density about 5 grams per centimeter cubed, the rock. Comets, maybe if you're lucky, 0.5 grams, usually 0.4. So this body isn't very big. It's big compared to you and me, but it's not big compared to a planet. It took billions and billions of these to build the planets. One of the most important reasons to look at comets is that you had to make comets first before you made planets. These guys are the building blocks of the solar system. In fact, when I was thinking about how I was going to present this talk, I look at them, and the time of the comets is really pretty much over. The comets that we see are actually, if you will, they've been in deep freeze for a long time. These guys have been in deep freeze out at the edge of our solar system, the disk of the solar system, what we call the Kuiper belt. And then they get scattered in every 10, 100,000 years. They last for a while in the inner system, and then they dissipate, they fall into the sun, they break up. They're gone, and then a new crop comes in. ISON's different. ISON's actually coming from deep freeze, and I'm going to show you this halfway to the next star, something we call the Oort Cloud. But comets really are, if you will, the dinosaur bones of solar system formation. They're relics from the era of 4.5 billion years ago when we were building the solar system. So I look at them as you will, as a history study. If you figure out how comets are, what they're made of and how they're put together, and I have some colleagues in the audience who are very good at figuring out their composition, then you can figure out what the recipe was for building the planets and how you and I could be having this conversation. On the right is the second object seen by the Deep Impact mission. We hit this Temple 1 here. We had a flyby spacecraft that watched the impact, and if we have time, I'll show you what we saw. Then it flew by, and it kept going around the sun, and then we brought it back to the Earth and retargeted it, and we sent it on to a second comet called Hartley 2. Now, if you're being uncharitable, Hartley 2 looks like a chicken bone. If you're being charitable, it looks like two blobs kind of stuck together. In fact, I'd forgotten, if you work on NASA missions, one of the cool things, besides all the cool stuff you get to do, if you come home after a successful mission, stuff shows up at your desk. And people leave you models and stuff. Although, Neil, you got one of these too, and you didn't work on the mission, so. Neil's a very good comet scientist, so he deserves one. So I don't mind passing this around, and you'll get an idea that this, we think, is a comet that's near the end of its life. So I want to talk a little bit about evolution of comets. Comets are the dirtiest snowball you ever threw as a kid. We don't think there's a rock at the center if you're a mean kid, okay? We think that very young comets are probably just random balls. And as they go around the sun, they start getting evolved. This comet's got probably depression pits and sinkholes in them because he's boiled and burbled in places and lost material. As they get older and older, they start getting eaten away in various places, and they have eruptions, and they have flows. This, for example, is actually the edge of a glacier. And there's a nice flow here, and there's another pit over here. Then as they get very old, they get eaten away around the equator, and your sphere turns actually into two blobs with, if you will, a gap or an etch in the equator. Imagine if the Earth was made of ice, and you know we're hottest to the equator, we would eventually turn into what looked like a dumbbell shape. Now that's one model. Another model is that this is just two comets stuck together at the very beginning of the solar system. We're not sure. We've only seen a few of these guys. But again, you'll notice that it's all very dark. We think this is a young comet, a middle-aged comet, and an old comet. These comets are all easy to get to, which means they're all in the plane of our solar system. I'll show you a little bit more about that later. They are not like Comet ISON. They're what we call Jupiter family comets, and they're in low inclination orbits. ISON is coming from much even farther away and a much deeper freeze. So let me give you the summary. In my old age, I've learned that I like to talk a lot. I like to show a lot of pretty pictures, so it's very good for me to actually show the bullets and get the points across first, just in case I put any of you to sleep or you run screaming for the hills. Okay, so comets are kilometer-sized mixtures of ice and rocky dust, so dirty snowballs. They are coherent bodies. When I first got into business, some folks seriously thought they might have been flying sandbanks or snowbanks. We don't think that anymore. They were formed at the dawn of the solar system, and they are what the planets were made from. So between the stars, you've got tiny little pieces of dust, maybe micron size or less, finer than your fine hair, or if you want to think about it, it's like the really fine dust in the bottom of your vacuum cleaner bag, much finer than your beach sand. That's what you build comets and planets of, in addition to molecules and atoms of gas. We don't know actually how you take those tiny little pieces of dust and gas and build up to larger than maybe BB to marble, millimeter to centimeter size. We know how you can stick them together when they're really small and they hit each other. But larger than that, they shouldn't stick. They should break up. So one of the mysteries of comets, and I should actually show you, this is Temple 1, by the way. I should walk this one around too. One of the mysteries of comets is simply how are they constructed, how do they hold together. We know that. We know how you put a comet together. We know how you can build planets. We know that once you have the comets, you can make the planets. Having a whole bunch of kilometer-sized bodies, we can make things grow larger. That's easy. So I'm also going to remember this talk is about not just comets, but also about ISON. So hundreds of Oort Cloud comets and 40 to 50 JFC comets come to perihelion in the inner solar system each year. ISON is not unique for a number of reasons. These comets I just showed you are not unique. In fact, we want them to be typical because we want to learn about the average comet. A few bust up every year, too. Hundreds of tiny sun-grazing comets from a previous big bust-up comet, formed what we call the Kreutz family, and they come by and hit the sun every year. There's actually now, I think there's on the order of a few thousand known Kreutz sun-grazer comets. What is interesting and exciting about ISON is that it's coming from the Oort Cloud with more than a year's notice, and it's going on top of the sun. We never get that much notice. We usually see these sun grazers maybe a few days to a week's notice. This thing has been on a long trajectory for a long time. It's going straight from deep freeze, where it was first formed and stored, straight into the furnace of the sun. And that's very interesting and exciting. And again, to cut to the chase, it's going to go close to the sun, that it's going to do that Bunsen burner experiment most everybody I've talked to has done as a kid in high school. You have the Bunsen burner flame, you take a little wire, and you put a little nodule of strontium or copper or cobalt or iron on it, and you put it in the flame and you see a beautiful color. ISON is going to get so close to the sun, it's going to boil not just the normal ices, but it's going to boil the dust, the refractory, the stuff that normally doesn't boil away. And that's going to give off characteristic emissions. And so some of us, myself included, are going to go to a solar telescope and we're going to look at those emissions. We're going to figure out what's in the part we usually can't test and figure out. And so that's pretty exciting too. That only happens once every 40 or 50 years. Okay, so I'm going to talk about the current crop of comets. We've had a Comet Elenin. You might remember last year we were all supposed to die horribly and not be able to come to this talk because of Comet Elenin. I'm glad to report that didn't happen. And the Mayans have been spared. Or maybe the only reason to worry if you were a Mayan. Panstarrs, which came earlier this year, which was actually hard to see from the ground. I'm a little bummed, I didn't see it very well from DC, but was a fantastic comet to astronomers, incredibly dusty, lots of structure, lots of things going on with it. And we have ISON now, and ISON is best if you're living on Mars or if you're living right on top of the sun. Neither place is known hangouts for humans. And we have a comet called Siding Spring that the Martians practiced. Because they practiced on ISON this year, Siding Springs was originally thought it was going to hit Mars next year in October. But it's now not going to hit Mars, but it's going to come so close that Mars is actually going to be in the comet's coma. And I'm going to show you what the comet's atmosphere looks like. So that's going to happen next October 19th. And the Martians, spacecraft folks, are a little worried what's that going to do to their spacecraft. And they're also excited about what they're going to get to see. Okay, other reasons to be interested in comets and the whole history. Remember, I like history. And I was fortunate enough to start out, and the reason I'm in astronomy is I started out working on the Cosmic Background Explorer. So I learned about cosmology and history of the universe. And I've been applying that locally. Well, when you look at comets, I've talked about how their history, they're relics from the beginning of the solar system. If you get a chance to look up, the moon is also a relic from the beginning of the solar system. And the moon was formed, we think, in a giant impact between a Mars-sized body and the Earth, when the Earth was about 80–90% formed, but was still accreting. So the moon itself is the relic of a giant impact onto the Earth. If you then look at the surface of the moon, you see that it's heavily, heavily cratered. And that's because we think 600–800 million years after the beginning of the Earth and the moon, that there was a giant storm of comets and asteroids that rained down on both of those bodies and pummeled them. And the Earth was just as heavily cratered as the moon is now, but we have weather and we have plate tectonics and we healed and we fixed things up. Why do you care about this? Well, it's the last evidence for the Great Shower, but it's also very interesting that within 100 million years, the first evidence of life after that shower shows up on the Earth. Many people think that they could have been that rain of asteroids and comets brought organics and water and brought what we see on the surface of the Earth now and took this dry molten rock that had basically had frozen lava and added the carbon and the water and the organics that allowed life to form. So this is a very interesting story, and it's one of the things that we like to look into. Okay, so I'm going to skip over the next statement. Comets and history, they go together. This is just a brief part of the timeline. The first evidence for seeing a comet in the records is 400 BC or so. It looks like it was Comet Halley by the Chinese. They kept excellent records. They mainly were worried about if a comet showed up in the sky, it was a very bad year to go start a war, or there would be a plague. But moving right along, we'll move quite quickly. There's lots and lots of interesting history in the middle of, in intervening time, but I'm being to be short for this talk's sake. In the 1700s, comets disproved Ptolemy and proved Newton. Newtonian gravity showed that bodies that move around the sun move on circles and ellipses and parabolas and hyperbolas. But the planets, and it could explain how the planets work, but so could Ptolemy and the crystal spheres. The planets weren't a very strong test of Newtonian gravity because they moved on roughly circles, slightly elongated, but not much. Comets, on the other hand, move on very long, elongated ellipses, and sometimes even almost parabolas. And they were very strong tests. And what Comet Halley was famous for, that Edmund Halley used Newtonian gravity to predict when Halley would return in the late 1600s, and lo and behold, it did. The other reason why comets were messing with Ptolemy and with Aristotle and the other system, the previous system, is that people could see stars through comets. Comets were ephemeral. They didn't fit in the fixed sky pattern, and it was clear that they were between the Earth and the stars. So if you will, they were a problem that needed to be addressed. And so comets actually helped bring in the new cosmology and understand that the sun was the center of the solar system, Newtonian gravity worked. Moving along, in the 1900s, we now started worrying about comets as relics. We realized they might have been relics of solar system formation, but also the dinosaur killers. People started getting scared about comets all over again, not with plagues and wars, but just the fact that they may have hit the Earth and caused problems. Another thing they worried about was they realized in 1910, when Halley's comet was last coming by the Earth, 1986 is the more recent version, it comes every 76 years, people had discovered HCN, hydrogen cyanide gas, in comets, or some evidence for it. And they started worried because the Earth was going through the tail of Halley. So if you go look this up on the internet, there was a huge run on gas masks. I kid you not. People were worried of dying horribly from comets, getting poisoned. They didn't. Gas mask people did very well. You can still see relics of these really ugly-looking green World War I gas masks around. And so that was the 1910s. In '65, Comet Kiyosaki, which could be a forebear of what ISON is going to do in next month, which third brightest comet of all time observed in the modern era, breaks up at the sun. The reason why it got so bright was it wasn't bad going into the sun, but then it broke up and released a huge amount of material. And that material all, just the same way that when you're smoking and you're under lights like this or track lights, there's not much material in the smoke, but it's really good and shiny and reflecting the light. Comets can do that. So ISON may very well have a Kiyosaki's fate. And a Kiyosaki was the last time we had a Bunsen burner comet that we brought close to the sun and were able to tell what it was made of. In '73, we had a disaster of a comet. Comet Kohoutek, which actually came from the Oort Cloud, looked very bright to begin with, then petered out, went around the sun, was kind of nice, and then came by the Earth and was a total dud in the sky, did almost the same thing that ISON seems to be doing now. It was touted incredibly by the press, and people became so disenchanted with comets for the next 15 or so years, they weren't interested at all. We want to avoid that. ISON, if anything, so Comet Kohoutek could very well have been a pristine and very interesting body from the beginning of the solar system as well, and it was scientifically, it was actually a very useful comet. First time we ever realized there may have been rock in comets. Some of the gases that we now know are very common in comets we first found in Kohoutek, as well as some of the people that I know of as if you will, standard bearers and some of the best comet scientists in the world. The people who taught me, this was one of their first comets. So we look at Kohoutek, I'm seeing very similar patterns, but we also want to make sure that we don't oversell this to the public. Comet ISON is going to be fantastic because, for many reasons. As I mentioned, it's going from the Oort Cloud, we're going to see it on top of the sun. We have 18 different spacecraft that we didn't have when Kohoutek was around, all looking at this comet. We have Keck looking at this comet. We have an incredible fleet of ground-based telescopes. We're going to, basically, if Kohoutek and ISON are the same type of comet, we're going to learn so much more just because we're ready and we're prepared. And because we had Kohoutek in the past and we can learn from history. In '86, '87, a Comet Halley reappeared and passed by. It wasn't a great apparition, it wasn't bad. It got a lot of press, it was kind of cool. I remember seeing it in the sky. I was lucky I saw more than just a little smudge. In '96, Hyakutake lit up the Hawaiian skies. And not only did I learn how to observe here, but I also have been very lucky to see Hyakutake, Hale, Bopp, and the Leonids. That's when I was doing my prime observing from on top of Mauna Kea. And they were just gorgeous. I will never forget them. I was very lucky. I think you guys have got some of the best stargazing in the world right here. And I was asking at dinner whether anybody was going to go up and actually see ISON from on top, and most folks just said, we can do it from our backyard, it's that nice. So I don't know, I would still encourage you. It seems to me like it's not real astronomy unless you go to 14,000 feet and lose a few brain cells and get a little grumpy, but it's all up to you. You are very fortunate to be living here. I'm also glad to be back here. In '97, I'll show you, Comet Hale Bopp was a beautiful comet, learned a lot. It's a fantastic comet for showing you the structure of comets. But it also, I'm going to show you a newspaper article. Osama Bin Laden saw that comet and actually saw it as a call to jihad. So even in modern days, people are seeing comets as prophecy. Okay. In 2012, Comet Elenin. Folks thought that was another prophetic comet that was going to destroy the world. In fact, instead it got destroyed. It kind of just went poof and went away. And in 2013, 2014, we're now here with Panstarrs. Earlier this year, we announced ISON, and Siding Springs can be exciting. And if I understand it, there's 2 or 3 more nice comets coming along now. There's a Lovejoy, and Neil, there's another one. What's the other one that's coming bright? Oh, there's another Panstarrs, I think. Yeah, we've got 2 or 3 more that could be coming along, brand new ones. But let me move on. But anyway, comets are always coming around the sun, and they're always very exciting. If you want to get an idea, we think there's roughly in the order of 1 million or so comets in the Oort Cloud and maybe a few 100,000 in the Kuiper belt. Those are very rough estimates. But the point I want to make is that there's not just one or two or a few thousand. There's hundreds of thousands to millions of those bodies. Okay, so here's an example of comet in history. Here's Comet Halley. This is a famous picture by Giotto of the manger scene, and there's your comet. The Bayeux Tapestry, which is actually, I've learned, is a very long thing, and you have to look really, really hard to find it, but there's your comet right there. And here's another comet here in medieval Europe. They have often been seen in the sky. Here's a famous picture of a comet over Paris in 1858. European paintings are rife with pictures of beautiful comets in the skies. This is what Hyakutake looked like to me in '96 going over the North Pole from Mauna Kea. It was gorgeous. It was about 20 degrees long. The full moon is half a degree long, so it was 40 times the width of the full moon in length. It was just beautiful. If you ever hear of a really bright comet, I'd encourage you to go up there and go look. Here's a Comet Bennett in 1970. This is over, looks like, I think, over some desert regions. And this is 2001 V1 NEAT, which is coming extremely close to the sun. Here's the sun here, and this is the width of the sun right here. And it's coming that close. And what was cool was this is one of the first comets we literally could see it going through a U-turn. I'm not going to show the movie, and watch it going around the sun. ISON is going to do this too. We're going to see it with the very same spacecraft. This is SOHO. If I stop talking and give you the introduction, I will get to that picture. All right, so here's Elenin. I think I'm going to skip through this, but basically Elenin was a bust. Don't believe everything you hear in the press. Elenin basically did what Schwarzmann-Wachmann 3 we saw in 2006, broke up into 57 pieces. Elenin did even more than that. By the way, comets break up. In case I haven't made the point well, comets are dirty snowballs, and they were put together in a relatively haphazard, very weak fashion in the swirling gas and dust that was moving around the sun in the very early part of the solar system. They were never taken to that point where you took your snowball and crunched it down and made it really hard, and even melted it, if you will, and pressed it and made it into ice. That didn't happen, we don't think. So comets are made not very well in the factory. There's no reason why they shouldn't fall apart some, especially when they come in for the first time by the sun and get heated and get stressed. Now, Schwarzmann-Wachmann 3 has been around the sun more than a few times, so it maybe took a while to stress it, but this isn't infrequent. We see maybe one or two comets a century fall apart like this. More spectacle inspiration. Here's your Hale Bopp. This is what Hale Bopp looked like from up on top of Mauna Kea. It was gorgeous. I remember Neil and I, when we first started working at APL over in Laurel, Maryland, went out and actually at sunset, we saw Comet McNaught. I never thought I'd see it. The sky was still yellow bright with very early sunset, and we saw this fantastically beautiful comet just in 2007. This is last year. This is Comet Lovejoy that went through the corona of the sun, broke up, then came out, and what you're seeing here is a dead comet stretched out across the sky. Reason I'm going, not only is this pretty and very recent, this is what ISON may look like to you in December. You have two outcomes that come with ISON. ISON could be a Kuhutek, where it's come in, it looked really good and precocious to begin with because it had stuff from the very beginning of the solar system that boiled off really easy, and that's all done, and now it's settling down into middle age. It's going to go by the sun, and it's going to bake some more and then go out, and then you guys are going to see nothing. Scientists will be happy, we'll have stuff to study, we'll be able to see the first time change in a comet before and after, and brand new material from the Oort Cloud. That's one outcome. Another outcome is it goes by the sun and it just falls apart, breaks up. It turns into this. You guys rejoice. Everybody from the ground sees a fantastic paintbrush across the sky. That could happen too. As an optimist, I think either way folks win. There is a compromise position. If ISON falls apart into 5 pieces, let's say, everybody wins. It creates a big puff of dust and gas, which will make a nice paintbrush on the sky, a little bit less than if it totally broke up. And 5 pieces is like we saw with Schwarzmann-Wachmann 3. We actually got to study the different pieces of this comet, and Neil, for example, was one of the scientists who showed that they all looked alike, and the comet looked like they were uniform throughout. And we'll be able to do that with ISON. So we'd like to do that too. So I see everybody could win. I have no clue what this comet's going to do. Absolutely none. And there's a lot of predictions out there. I'm going to skip over this because it didn't project. This is Panstarrs. If you were lucky, you could see a really faint little comet over there. It wasn't very bright. On the other hand, it was gorgeous to telescopes. This is an example. That's a huge, dusty comet. Very exciting. Okay, so I promised this. This is Hale Bopp in the sky. This is from The Independent, 22 March, 1997. Osama Bin Laden, unwilling to da-da-da. Rifles beside them saw the comet, Alula Akbar, bleak landscape, sky with a fiery tail unseen since the time of the pharaohs. It was, I learned later, the Hale-Bopp comet. They say after a comet there will be a great war. And this is serious to some folks, still. Okay, so let's move it along. Let's talk a little bit about the history of ISON, then I'll go back and talk a little bit more about comets and give you some more nuts and bolts detail. So I am not very good with Russian, and so I'm sure I'm butchering these guys' names. Discovered in September 21st, 2012 by Vitaly Nevsky, that's the easy one, and Artyom Novichnok. Any Russians in the audience? You want to try that one? Okay. So they found, with a rather small telescope, a 0.4 meter telescope, at the International Scientific Optical Network, ISON. The Russians have their own acronyms. This is impressive. It isn't just Americans and NASA do it. In a small town, which is, this kind of looks like something from Facebook, in southern Caucasus, so south central Russia. And the joke I make is that every now and then they let them out of their little box. What I find amazing, and this is some of the things that impresses me, I'm a pretty good astronomer, but I'm in the good, this is their discovery image. That's ISON. These guys were good enough to know that that blob there didn't belong. It's impressive. They knew the sky that well. And so they deserve a lot of attention. They aren't getting as much as Hale and Bopp got for that comet in '96, but I do understand that there's some film crews going out there. If folks come to talk to us, we send them out their way too. And so it'd be very nice to hear from them. I haven't met them yet, I would like to. Comet ISON, since this detection has grown, here's a beautiful image from, it didn't project very well. There's actually, it's a shame, there's a beautiful long tail on my screen here. So this is from Arizona just last week, and the tail should go out to about yay. And this beautiful green color is real. The comet has got a lot of what we call C2 and CN radicals in it. And so if you were to go out and look at it, do you remember Yakutaki, that color? Comets, I was realizing, having talked to some colleagues today, have different colors. So these are real colors. You'll notice they're kind of yellowish and whitish. That tends to be the dust. Hale-Bopp had a beautiful glowing blue gas tail, which is unusual. And that's false color, so don't look at that. This color of Yakutaki, I believe this is real color. So Yakutaki was also a greenish comet. A lot of dust here too, that's the yellowish white. So ISON is looking like it's got a very nice linear, simple dust tail. Oh, darn it, it really isn't coming out. Right here, yellowish white, and a big fat gas color, which is a beautiful green color. It's still, you can't see with the naked eye, but telescopes, it's not too hard. So this was just taken, as I said, Arizona last week. It wasn't very difficult to get, or 2 weeks ago, I should say. Okay, the reason I'm talking to you, and we're doing a lot of work and attention on this. This is that ISON observing campaign I mentioned. We have a website. The reason why I'm putting this up is that we're doing our best job to facilitate, explain, get the facts out, and then let you guys go do what you want to do. I've gone on record as saying I want to get every telescope in the solar system looking at this comet if I can. That includes amateurs, includes people with binoculars, actually, is a pretty easy way to see comets, especially big and diffuse ones like this one. It's a big fat fuzzball in some places. So I would recommend, if you want to learn more about our comet, about Comet ISON, you can go to this page. We have facts for the latest what's going on with it. We have people blogging, professional astronomers, and there's contact place if you want to go and send me an email. That's one of the contacts. Please do. Okay, so let's get back and talk a little about the nitty-gritty of comets. I mentioned that comets were a good test of Newtonian gravity. That's because they have come on very different orbits. Did it? Oh, good Lord, pardon me. Did the orb circles of the planets? Can you see them? Very barely. I'm sorry. All right, well, this isn't actually, that's what's more circular comet, but the planets all go around in circles, and you can barely see it here, but that's, pardon me. This is a comet orbit. You see how it's much more elongated than this circle? That's typical comet orbit. There's another one down here. That's Halley, that's Yakutaki. And this slide's not working because it's not projecting. Is this one projecting? Good. Okay, this is Comet ISON itself. All right, and Comet ISON, as I'm going to show you in the next slide, I'm going to skip here and go back. Comet ISON is coming from what we call the Oort Cloud. There's two collections of comets. This usually takes a minute or two to explain. But the short answer is that if this is the sun here, and this is the Earth here, and that's the outer planets, Comet ISON is coming from this huge distributed sphere of comets that go in all directions and that extend halfway to the next star. And this is actually not to scale. These planet orbits should be a lot smaller. And I have some other slides that will show you a little bit better. But Comet ISON is coming from very, very, very far away. And it's not coming from the plane of the solar system. That would be the easy way to go by Mars, Venus, Mercury, the Earth, and the Sun really close, which ISON is doing. And that's one of the reasons why ISON is extraordinary. ISON's coming from up here, coming from 62 degrees perpendicular. The way I like to think of the solar system is like a record, with the planets going around the grooves of the record almost in circles. And the easy way to get near the planets is to go along the groove of the record. ISON's coming from here. It's just a really lucky orbit. Okay. These comets were stored here at the very beginning of the solar system when they tried and failed to become part of Jupiter, Uranus, Saturn, and Neptune. Billions and billions of their brothers and sisters coalesced and formed those planets. Remember, comets are the building bones of the planets. But some of them missed. A whole bunch of those guys that got thrown out in all directions never came back. They got thrown out to either interstellar space or got captured by the next star over in our birth cloud. However, millions and millions of them got put into the Oort Cloud, and that's where ISON has been since it was formed. Okay, so that's the orbit it's coming in on. ISON is coming in, and hopefully this projects well, and is coming close by Mars. Why is it down there? It should be up here, sorry. Coming close by Mars, and then coming into Mercury. So Mars happened, that was October 1st. Mercury is November 19th, that's the closest approach there. Then it's going to go by the Sun on Thanksgiving. Then it's going to come out, and it's going to come by the Earth the day after Christmas, and it'll be pretty close to Venus, too, about the same time. So remember the 2 dates, Thanksgiving and the day after Christmas, ISON is also going to be a holiday comet. And for those of us who are astronomers, it's going to be the comet that stole our holidays. But for you guys, it's going to be more like, hey, you're finished with the family, you ate a nice dinner, let's go outside and let's see if we can what we can see. Thanksgiving, when it's on top of the Sun, is when it will be brightest as well. And it's going to be very bright. It's going to be as bright as Yakutaki or Halley. The problem is it's going to be on top of the Sun. Okay? So the good news is that ISON will get really bright. The bad news is it's going to be right next to the Sun. And that's not, you can't see the full moon next to the Sun either. So it's going to be a little challenging. The solar telescopes that I'll talk about a little bit later and the solar spacecraft are going to go to town on it. It's going to be a fantastic show. If it breaks up on the Sun and comes out, the first few weeks of December, and maybe even into Christmas, it's going to be gorgeous. Okay, so here's that plot again. Here's, by the way, some examples of imagery of ISON. This is Hubble Space Telescope in April, May. And beautiful structure here, very simple. This is the coma here, and here's our linear tail. This is Spitzer Space Telescope. Here's that nice dust tail. And here's a nice gas coma I was talking about. We saw this in June, and it's getting better and better as ISON gets closer to the Sun. All right, so this is the real reason, in a nutshell, one slide, why you care about ISON. First passage of comet through an inner solar system since its formation and ejection into the Oort Cloud. I just mentioned that. Likely contains some of the most pristine material because of that. Basically, it's a good sample. It's a dinosaur bone, if you will, of the early solar system that was built before the planets were fully built. It also gives us, we have detailed orbital knowledge for this Oort Cloud comet, which we've studied very long. And I want you to think also that while ISON looks like it just showed up, the orbit it's on is extremely elongated and extended, and actually it takes millions of years for it to go around this orbit. So ISON really started this travel, this journey into the inner solar system, probably around the dawn of man. So 3 or 4 million years ago. And I'm being generous with anything that really looked like a man and walked on 2 legs. So it's interesting to think that ISON, we're here today, we're ready to see this comet. Even better than Kahutek 40 years ago, but ISON has been coming into the inner solar system for millions of years. And most likely was perturbed by a passing star, we think. So it's on a sun-grazing orbit, as I mentioned, with more than 1 year of lead time for us to get ready and to get to solar telescopes, which don't normally look at comets. And as I mentioned, Thanksgiving perihelion, it is going to come within 2.7 R-sun of the center of the Sun. That's so close that you actually have to worry about the width of the Sun. It's coming within 1.7 R-sun, radius of the Sun, of the surface of the Sun. Okay, so it's coming pretty darn close, it's about 1 million kilometers. The local temperature is going to be a few thousand degrees. It's going to have it had its close encounter with Mars at 0.07 AU. Mars had the best seat in the solar system for a few weeks. That was October 1st. This is coming within 0.24 AU, where an AU is the distance between the Earth and the Sun, or 93 million miles. It's coming within that 0.24 AU of Mercury on November 19th. It's coming next to the Sun, as I mentioned, on Thanksgiving. Earth is going to be day after Christmas, and so is Venus. And one of the things I was approached, and one of the reasons it was good to be part of this committee and talking to everybody, is I hadn't realized it's coming almost as close to Venus as the Earth. We hadn't appreciated that. So we talked to Venus Express. And I should back up and say we have 5 different spacecraft, rovers on the ground and orbiting spacecraft, looked at the comet from Mars. One is orbiting now around Mercury called Messenger. It's going to look at the comet. Sol, we have 4 spacecraft looking 24/7 at the sun. Earth, we have the fleet of spacecraft, of course, the ground-based telescopes. There's also, ESA has the Venus Express at Venus that's going to look at the comet. So there's quite an extensive campaign studying the comet. So as I mentioned, the last time this happened was in '65. So we've learned a lot. We've got a lot going for us. I showed that. Here's where we are now. We've been watching this very carefully. ISON is not exactly behaving the way we'd expect. If you want a model comet that was turning on and getting higher and higher and brighter as it went to the sun, it would do this black line here. ISON's doing the red line. It was scaring us a little bit that it wasn't going to do anything, but now it's starting to curve up, and if you look very carefully, I know the projector's a little tough, it's actually up here right now. So ISON is really starting to peak up, and in the next month, it's going to become that boomer and then come down again. What's curious and worrisome slightly is that this is Hale Bopp's behavior in 96, 97, really bright. This is what ISON is doing, and this is what Kohoutek did. ISON seems to be following Kohoutek more than Hale Bopp. Brand new as of this week and last week, this is the latest Hubble Space Telescope image of ISON. It looks like we have a beautiful comet, a nice little nucleus hidden in here, a nice coma and a dust tail. Okay, fine, looks stable. At least 3 different scientists have gone on record now saying ISON is a goner. It's done. It's going to break up and fragment and disrupt even before it gets to the sun, just like Elenin did. And here's a brand new plot. This is from Nicolas Bouvet, a French colleague of ours, who is arguing, and I know there's lots of squiggly lines here, but basically the long story short is this red dashed line is a line a comet has to get brighter than if it wants to survive and not do, or that's Elenin. Here's ISON. We're here. All right, just to give you contrast, here's McNaught, that really bright one in the sky. Here's Panstarrs even. Here's Kohoutek is the pink guy. Kohoutek stayed above this line. So ISON is here. If we extrapolate, we get over to here, and then we fall off the chart. So this is one scientist saying we're not even going to make it that far. We have another one who's saying with 100% certainty that ISON's light curve looks just like one of these guys and it's going to die. We have Hubble and Spitzer and Keck all saying the comet looks funny, nice and stable and looks fine. So we don't know what's going on exactly. It's any man's game, any woman's game. This is what ISON's going to look like when it goes by the sun. Remember I showed you that previous version, that beautiful comet, neat. I know I'm showing you a lot of comets, but that beautiful one that looked like it was puffing up right near the sun. This is ISON coming in, going to go out. It's going to take 3 or 4 days to do it. And this is the size of the sun. This is an artificial disk put on the sun by SOHO in order to hide the sun when making observations. The blue is where you get real data. The red and the black here is just superimposed. It's done in Photoshop. So ISON is going to come in. It's going to go that close to the center of the sun, and it's going to come out again. Lovejoy last year came in even closer, and all the dust tail, all the dust and all the coma evaporated. It became a bare nucleus, and then it had to go out again, and then the tail reappeared. We're expecting the same thing. That's the blowtorch or the Bunsen burner experiment I was talking about. So this is what's going to happen with ISON. Unless you're really, really good and have some sort of smoky glass vision, you're going to have a tough time seeing the comet here. But special observers can do that, and certainly our spacecraft can do that. And if it breaks up, most likely it'll break up somewhere in here. Give you an idea of what our solar spacecraft are going to see. Lots of words here, but more importantly, here's SOHO. That's, again, the imagery I just showed you before and with V1 NEAT. Here's an example of Comet Lovejoy. Here the comet is coming in. I hope I can see. This isn't projecting very well. Here's Lovejoy's head, and it's lost almost all of its dust, and here its tail. It's reappearing. So it's lost all the stuff in here, and that's the evaporating dust. So SOHO saw Lovejoy. SDO, this is Lovejoy actually going through the sun's corona. So again, think of something the size of Mauna Kea, maybe there, and it's got a tail that's relatively long. It's moving at 650 kilometers per second, also known as 0.002 times the speed of light when it's that close to the sun. And the sun's giant. The sun's a million times bigger than the Earth. So it's amazing we could see anything at all. Mauna Kea, sun. But still, SDO was able to pick this out. Just impressive. And here's stereo, which is also going to see it. By the way, this is that comet Panstarrs, which I said was lousy from the sky, from the ground. This comet is just gorgeous in dust, and there's just a thesis or two. If there are any people in the audience who want to go back to comet school, I've got a research project for you. And I should also mention that if ISON breaks up, it'll start looking not like that very simple tail I was showing you before. See that very beautiful, just very simple little ball here, linear tail? If ISON starts to break up, it's going to start looking like this shaggy little beast here. We haven't seen any evidence for that. And just to put an exclamation point on it, here's Lovejoy again. This is what it looked like. If ISON breaks up, this is what you can expect. And somebody just made this plot, and I grabbed the slide. That's my birthday. So this is what ISON would look like if it gives everybody a present. Okay, and just to remind you that ISON's great, but next year, about the same time, we're going to have a comet that's literally going to put Mars in its atmosphere. So some of us are practicing with our spacecraft. And just to give you an idea, the equivalent, what a Martian spacecraft just had to do is the equivalent of taking your GOES weather satellite that takes your images of the nightly weather, when typhoons or whatever the clouds or the rainstorms that are going to come in and hit you from across the Pacific, and asking it to look up and look at a galaxy or a star. It's not used to doing that. It's not used to looking at something that's faint and in a dark sky. It's used to looking at a really bright Earth. So the Martians did pretty good for what they had. And they detected it with the MRO high-rise camera. That's the one that followed MSL all the way down and found the rovers on the surface of Mars. And they detected it roughly 10 times. And they put a much better limit on the size of the nucleus. It's much smaller. Okay. Now let's away from history and away from current topics. This is a beautiful cartoon I got many years ago when I was working at Space Telescope from Bob Brown, and the cool thing about it is here's the cartoon, and here's the data actually showing you the different stages. About 5 billion years ago, intersecting supernova shock waves in our galaxy caused a giant molecular cloud, a collection of dust and gas, to start collapsing. Once it starts collapsing, it gets runaway growth and starts falling together and makes a little baby star, a protostar at the center. It's a very messy process. That's why it takes about 5 solar masses to do it. Most of the mass isn't going to go into our sun. Instead, a lot of it gets actually blown out in what we call bipolar outflow into jets. And here's an example of that. TW Hydra shows them in DG Tau. Previous, I should show you, these are what are called propylids. These are in Orion. If you all know where Orion's sword is, and the nebula down there, it's a nice local or nearby region of star formation. These are actually little baby protostars, and they're cocoons of gas forming. The collapse here happens about 10,000 years. This takes only about 100,000 years. It's pretty fast. Then in the next million years or two, that's when you make your comets. Okay? Most of the materials fall into the center of the sun, 99% or so. There's a fraction of percent is still left in a disk, a swirling disk. And the swirling disk happens basically because this cloud starts to begin with, has some net angular momentum, and as it collapses, it goes away from that spherical symmetry into a system that's got a net spin and a cylindrical symmetry. Okay, so you make your comets in the first million years or two, and the comets collect and start forming the giant planets. And that's the era in that the comets are sampling, if you will. That happens and we think in 3 to 5 million years. Gas dissipates in the disk, but you're left with a lot of dust. The dust then build the rocky planets in the next 30 to 100 million years. That's when you make the Earth and Mercury and Moon and Venus. It takes longer to make these guys because there's less dust than there was dust plus gas early on. And these bodies are smaller. And finally, after about 100 million years, you clean all this out, and you're left with what we call a mature solar system, what we have today, and with some relic bodies like the asteroids and the comets. So this is the history, and it's really interesting to watch, and I'm very lucky to be working at a time when we can start testing these different parts of the evolutionary history. Very messy, busy, but the important thing to point out here is that things weren't just sitting with a protostar at the center and just quietly swirling stuff around in a disk, which we used to think. There's actually lots and lots of flow. What we see in comets today looks like a mix of ices and gases that formed at very low temperatures, very outside the solar system. But the rocks and the dust that we see in comets look like they've been inside the orbit of Mercury, right next to the sun, baked and boiled and processed and crystallized. Very interesting mix. So another way also to look at it is that those nice little planets that we live on, like our Earth, current models are that they weren't just sitting there and slowly swirling around and just collecting gas and dust. More like they were actually the toughest and badass survivors of a very violent process of planet formation. All the planets we see today basically said to all the other bodies, the Moon and Mars-sized bodies that were growing, you either join me or you get the heck out of Dodge. And it's called what we call oligarchic growth, and there was a massive collision epic. And the Earth and the Moon survived out of that. And that Moon collision I talked about, that was actually one of the last stages of forming the Earth. So, the comets that we have today, remember, they're made in the first few million years of the solar system. Where are they and where do they come from? Well, there's two big collections of comets, and I'm not sure how well this is projecting. This is a shame. This is due to Don Yeomans. We have the Kuiper Belt comets and the Oort Cloud comets. Remember I told you the solar system is sort of like an LP record with the planets moving around in the grooves? Well, the record has to stop somewhere. In other words, the solar system has an edge, or a rough edge. It isn't really hard, but it kind of peters out, and it just becomes the space between the stars. At the very edge of the solar system, there's ice and gas and dust, but there isn't too much. There isn't enough to make a planet. But there are enough to make comets and Kuiper belt, and a little bigger than your average everyday 1 kilometer, a few kilometers like comets, to make the Kuiper belt objects. And those are the guys that we see today. And they're at the edge, if you will, of the record. And every now and then they get perturbed and spiraled in, and they become our short period comets. And we know of a few hundred of those. Those are the ones that are easy for us to visit with our spacecraft, and that's the Wild 2 and the Tempel 1s and the Hartley 2s that I showed you and are moving away around the audience. That's not ISON. The other guys, so these guys formed at the edge of the solar system. This is where it gets confusing. The Oort Cloud comets actually were formed inside the Kuiper belt comets. They formed between Jupiter and Neptune, and as I mentioned before, they tried to coalesce and become part of the giant planets. Billions of them did. Millions of them did, missed barely, and then got these gravity assists and got thrown all the way all kinds of different directions. So they formed inside the Kuiper belt comets, but then got thrown outside. A lot of them got thrown away, never came back, but the ones that did come back and went into lower energy orbits actually held the relics, if you will, of what was going on in the space in that early solar system disk between Jupiter and Neptune. Remember, the Kuiper belt guys actually hold the record of what's farther out. One of the holy grails of comet science is to try and look at and see if we see any chemical differences or size differences or construction differences between these two kinds of comets. We're still working on it. This is one of those Power 10 slides. I hope, again, that it projected. So here, if you will, is the inner solar system. Here's Mercury, Moon, Mars, Venus, the asteroid belt, and here's the orbit of Jupiter. Okay, so this is the space that we're used to working in. Then you project that out, and here's the outer solar system. You start bringing in the Kuiper belt objects. Then you project that out and the 20,000 AU, and now you're starting to get the inner edge of the Oort cloud, and now the outer edge of the Oort cloud. So Comet ISON, and actually another way of putting this, I just was fortunate in Denver, I was at a DPS talk where they're talking about how Voyager 1, I believe it was, has just left the solar system. It hasn't. It has and it hasn't. It has left the heliosphere. Voyager 1 is still inside the Oort cloud. And then it dawned on me, and I know I should have realized this, I'm a slow scientist, the Oort cloud comets are living in interstellar space for many reasons. They are exposed to the light and the radiation that's outside the sun's environment. So our Comet ISON has been exposed to a pretty tough environment for a long time. I think I'll skip over this. I just want to show you here, these are images of what we call debris disks. Keck does a lot of this work. And every one of these you see here are images of very large Kuiper belts and Oort clouds. We don't have the potential to image asteroid belts, but what you're seeing here are relic belts around these young and medium-aged stars, which is pretty cool. We know that there are comets, Kuiper belts, and Oort clouds around other stars. I think I'll skip over this. This is work that I really like to talk about. This is a star that looks like it's having a late heavy bombardment, and this is a lot of the spectroscopy I do, but we don't have time. Okay. Here's Hale Bopp. Here's that classic picture I was going to show you. So Comet Hale Bopp is the largest comet we've seen in the modern era, somewhere between 20 and 50 kilometers radius nucleus. Big guy. The average comet we think is on the order of a kilometer or so. Again, just to remind you. So he's the operative, or if you will, the body that's really doing all the business is sitting down there. Around that body, as it gets close to the sun, because it's made of water, ice, and carbon monoxide, and carbon dioxide, and methanol, and ammonia, and a few other ices. It gets close to the sun, and it doesn't melt, it boils. So for folks who want a similar process, if you've ever gone to the ice cream truck, I don't know if you guys have ice cream trucks in Hawaii like we still do back home, and you go there in summer, which is every day here, and you ask for an ice cream, and the gentleman opens up the freezer, and you see a puff of smoke, what looks like smoke come out. What you're really seeing is subliming carbon dioxide gas, because he's using bricks of carbon dioxide, solid carbon dioxide, the same stuff that you breathe out, that plants breathe in and turn into leaves and roots and things. And he's using that as refrigerant. And basically, it doesn't melt, it boils. It just goes straight from solid to gas. If you've ever been on top of Mauna Kea after snow, you might have been lucky to see actually snow boil. I've been up there. I've seen it in Colorado. I've definitely seen it on top of Mauna Kea, where it doesn't bother melting. The pressure is low enough there, it will actually just boil straight off. That's what the comet's doing. It's boiling off the ices. The dust that's trapped in the ice also boils off with it. Gets blown out at about half a kilometer or so per second, so wind of a few hundred miles an hour, and gets blown off, and it forms what's called the coma, and that's an atmosphere around the nucleus. If the nucleus stops boiling, all of this goes away. So remember those kind of dark blobs I showed you at the very beginning? That's the operative. That's your comet. It's always there. The only time the comet, as we say, becomes active and creates these tails is when it starts boiling. ISON's beginning to do that more and more often now. These tails, counterintuitively, can actually be some of the largest things in the solar system. The dust and the gas tails can extend many AU, many times the distance between the Earth and the Sun, so many hundreds of millions of miles, even though the comet is a tiny little thing down here, just a few kilometers across. So, and there's two typical tails. The dust gets picked up, and actually it's so fine, remember it's that really fine micron-sized dust, it gets blown away by solar radiation pressure, the light from the sun, and blasted away from the sun. So the sun's pretty much down here. And then the gas from the comet gets ionized by the UV light from the sun, and then it gets picked up by the solar wind. And here's another piece of interesting comet science. In 1950, a gentleman named Biermann, a German scientist, noticed that the ion tails, or gas ion tails for comets, seemed to be pointing a little bit off the solar direction, but roughly he could explain them by what we call the aberration, the velocity of the comet around the sun. Long story short, he can explain the dust as the radiation pressure. He proposed that there was a wind coming from the sun that was picking up these gas particles and then accelerating them. In other words, comets were used to actually predict the solar wind in 1950. Yet another piece of comet history. It's really kind of interesting to see how the history just falls out from studying comets. Okay, I showed you 3 nuclei at the beginning of this talk. This is the first image we ever had of a comet nucleus. This is Comet Halley. It's a relatively big one. It's about 10 kilometers this a ways. And the amazing thing, there's a few oldsters in the audience like me. This was taken with a single row of CCD pixels on a spacecraft spinning a few times a second. Maybe a few times a minute. You have to check me on that. But so this is literally, this is not a framing camera that we're all used to, we all have sitting in our pockets now. This was a very primitive camera. And Alan Delamere, the fellow who just used the HiRISE instrument to find ISON from Mars, is famous for having put this together within a few hours, I believe, of the Giotto spacecraft flying by Halley. So the nucleus is roughly here. It's a little hard to see the darker bits. The sun is up here. And what you're seeing, this is the terminator. Okay, so this is night is below the green, and this is day. And these are jets that are blasting up towards the sun. The brightest points in this image are not on the nucleus. They're actually here. And this is one of the things, by the way, that gave us with deep impact fits. Remember, we had to target and hit a comet at 6 miles a second. If we just went for the brightest image, or pixel in our image of Comet Tempel 1, we were worried that we would hit a jet, we'd miss the comet totally. So we had to spend a lot of time making a smart impacting algorithm, but it worked. Second comet we ever flew by was Comet Borrelly, 2001. This is by the DS-1 spacecraft. And Comet Borrelly, the best way to describe it is it kind of looks, it's like that 2-part that I showed you with Hartley 2. It also kind of looks like a bent shoe, with this part being bent up a little bit. And it looks like 2 lobes stuck together. If you look at Halley in a different stretch, it also looks like it could be 2 lobes stuck together. So we now know of 3 comets, I would argue, that look like Borrelly, Hartley 2, and this all look roughly the same. Stardust looks like a melon, looks like it's maybe the youngest. And Tempel 1 still making it around. So I would argue is that maybe, and remember, I'm arguing from a number of 5, and astronomers are good at doing this, and come back in a little whiles, but we're beginning to feel the elephant, and maybe what we're seeing here is an evolutionary progression. Very young comet, somewhat middle-aged, and ancient comet about to die. That's today's working theory. It'd be nice to come back in 100 years and have another 5 comets. Lots of plots here. I don't want to go through them, but I do want to, other than to show you that this is the size of comets, and this is the frequency of we see them. You'll notice the peak here is around 1-ish kilometer. This is a Spitzer survey of 100 different comets, and it falls off drastically. To point out is the Halley's over here, Hale Bopp is over here. They're very exceptional comets. Even Tempel 1 and Vil 2 are sitting around, they're around here. So your average comet is about here. We think ISON is maybe up here. It's probably very average in size. So the big bright boomers that we all know and love and go look after are exceptional. This is a very nice montage. Very slowly, ESA and NASA and JAXA are beginning to actually fly by a whole bunch of our little bodies, they're relics, dinosaur bones. And over here, everybody over there, those are all the asteroids. And we don't even have Vesta on here. Vesta would be bigger than this whole image. Down over here, those are our 5 comets. So comets are little guys, and they come in various shapes. But these are the big rocks, okay, either carbonaceous or metallic or stony, and here's our little primitive snowballs. Okay, how am I doing on time? Am I done? I can talk about deep impact real fast if I have a chance. I was lucky enough to get into really get seriously in the comet business that as I mentioned, we built the spacecraft. This is actually what deep impact looked like. I was at the IRTF on top of Mauna Kea when this happened. It was a really exciting time, and then we had more than 80 telescopes around the world looking at this. Probably more than we'll get for ISON, but that was just a fantastic time. And I learned from these campaigns. I learned from Karen Meach and Mike Ahern how they set this up, and we're doing that with ISON. I will also go on record to say I was a very actually disappointed, unhappy person when Deep Impact happened. And it's a funny story. I think it's worth 30 seconds. Karen Meach and I were on top of Mauna Kea, and she had gotten herself a brick of this is back in the old days, a cell phone that could talk to satellites and could talk to anywhere in the world. So she didn't have to worry about cell phone coverage up on top of the mountain. And we both were looking up in the sky with binoculars, and we were waiting for a giant new star, like the Star of Bethlehem, to show up, because we had predicted that when Deep Impact hit Temple 1, it was going to make a huge cloud of dust that would catch the sunlight, and we could see it from the Earth. Didn't see squat. We hit the comet. We threw out huge amounts of dust. We put out so much dust we could never see inside the crater. That was actually one of the primary goals of Deep Impact, was to make a crater and watch how it developed so we could learn about the gravity and the structure and the strength of this body, do an excavation. We didn't see anything. So I went in, I was real grumpy. I went and sat down, and suddenly we're sitting here, we're going back to our observing. We did actually see a jump, and I think Neil was there working with us, and we got some good data from the IRTF, and we heard our folks over in the Keck were doing well too. In fact, Anita Cochran, who's observing ISON this week, was over there. Anyway, long story short is then we saw people jumping up and down and screaming on the TV monitor at JPL, and they took the data about 7 or 8 minutes and then 2 minutes to go through the pipeline, and they were just exuberant because they had just seen the data from the spacecraft. So it got better. But that was my original. On the other hand, I did manage to convince the IRTF director to let me drink a celebratory beer, at least a little bit, which you're not allowed to do on the summit. But for that reason only, and for that one reason, I think we were allowed to celebrate a little bit. So this is actually where we hit on the comet. I mentioned earlier, I showed you those 2 craters that we use, and we hit, we think, right here. Now, if you think about it, the last place you want to hit on a piece of virgin solar system territory that you think is pristine from the beginning of the solar system is someplace that's already been hit, and possibly boiled and baked and processed and smushed and changed. But on the other hand, we hit the comet. So you take what you can get. Most likely, the argument is we think we hit, and we may have blown away actually this little dark bit here, and it actually could be something sticking out, maybe a berm or even a pillar. It's not clear. But what we did was we made, and then we also had the Sierra Club, if I remember, and the Environmental Defense Fund getting really angry at us because we were hitting a piece of virgin solar system territory. Well, and our response was, well, craters happen. And remember, the comet ran over us. Now, literally, we did get in one of the comet. It looks like we hit it, but literally, we kind of got in front of it. The truth of the matter is that craters do happen, but not usually with silicon-based circuit boards and hydrazine fuel tanks. But we really didn't do much to Temple 1. I was lucky because I was tasked by Mike Ahern, the principal investigator, to use the Spitzer Space Telescope to look at this comet. This is what the dust looked like before we hit Temple 1. It was boring. Couldn't see anything. It's because of big, large clouds. This, by the way, is Hale Bopp's. It's got the red one's Hale Bopp, sorry. This one's Hale Bopp's, which was just a gorgeous comet, was the gold standard. People learned a lot before then. This is what the dust from Temple 1 looked like after we hit it. We basically took those big clots and turned them into tiny little pieces, rather than the dust bunnies, which the dust collects in the comets, we made it into the individual little tiny bits. And we got one of the best dust spectra, astrophysical dust spectra in the world. I'm very lucky, and I had a great time learning about this. And from this, I've been doing for the last 5 years, learning about what the refractories are in comets and asteroids, and also around nearby stars that are building their own planets. What was really interesting was we made a prediction of what's in the comet, and then Stardust went to another comet, Build 2, took what I like to call rock jello, aerogel. It's very light. It's really fun stuff. If you ever take a piece and whack it around in a little tube, it looks like jello, but it sounds like a piece of glass is breaking. It's very strange. And it's very undense, and its job was to take dust that was moving at roughly 4 miles a second, the spacecraft was going that fast versus the comet, and make it decelerate and stop in a millimeter or 2, and make it survive. So they actually flew a centimeter thick worth of aerogel. They only used this much, pretty much. And so going from 4 miles a second to 0 in that space, you can imagine sometimes you got a little hot. So the amazing thing is they actually collected a lot of very good samples. And what was really nice was we used what we call remote sensing. We looked at the Deep Impact mission experiment. We used Hubble, we used Spitzer, we used Chandra, we used all kinds of ground-based telescopes. We predicted and thought and explained what we thought was there, but there is nothing like having actual bits and pieces of stuff in the lab. And so we got ground truth, and that was fantastic. And This is just a little plot of all the things we think are in comets in the solids. Okay, you've got water ice. That's the carbon dioxide I was mentioning was boiling off. That's the blinding carbon dioxide ice. You've got soot. You've got amorphous carbon and PAS, also the stuff that you on burnt carbon or also in the atmosphere around LA in a bad smog day. You've got olivines. So this is basic silicates and pyroxenes. A little bit of carbonates, lots of metal sulfide like pyrite. A little bit different than pyrite, but like pyrite. Maybe native iron, and maybe some clays. And these elements, while they seem like a lot, this is the basic stuff that we think that the solar system was formed from. Kind of cool. I'll read you the recipe later. I do want to move on, but basically take 1 part of this, 3 parts of that, 5 parts of that, mix it in a cold, dark place, wait for 4.5 billion years. The other thing that was cool about this was, so we started getting a handle on the composition, then we realized that we looked at the silicates I mentioned, the olivines and the pyroxenes. They're not glassy like we see between the stars. They've been changed. They've turned into crystalline. So imagine you take window glass and you were to heat treat it and you turn it into a quartz crystal. That's the equivalent. It's not easy to do that. You actually have to heat it up and you have to cool it slowly. What this told us almost immediately was that even though comets, as far as we knew, formed at the edge of the solar system, or at closest maybe Jupiter, they had parts of them, the rocky parts, had to have been closer to the sun than the orbit of Mercury today. So that told us that the solar system had to be rotating and mixing and wasn't just sitting there statically, slowly going around the sun and coalescing. So that's why I showed you that very busy slide a lot earlier on where the arrow's going all which way, but there's lots of mixing going on. So comets are 1 part, if you will, fire, stuff that's been into the sun and came out again, and another part ice that's coalesced far away from the sun. Okay, depends on how much you guys want to keep hearing. There's plenty more. This is Hartley 2. So I had the good fortune to be at JPL for the second comet that Deep Impact went to. And yes, it's nerve-wracking, and you remember there's a light travel time. Even though you say, oh, we just went to the comet, it still takes you about 5 or 10 minutes for the data to come down and to process, so you're always on pins and needles. But it was fantastic seeing this come in. And again, JPL did a fantastic job. We built this spacecraft at Ball Aerospace. Marilyn oversaw the project. JPL had to take a spacecraft, I can finish up that, and basically do this with it. And turn around while it's moving roughly 12 kilometers per second, so 7 miles a second, past this comet and reduce all this data and see that. And what we saw was an extremely different looking comet, a very small one, what we also call hyperactive, which I think is near the end of its life and is reaching down into its very core, and everything is coming off of this comet. The other really important thing that came out of this is that we started, this by the way is a movie which won't run, but that is all dust. And this is actually the shadow of sunlight from the nucleus is showing a shadow on the dust. When we came up close, oh, darn it doesn't show up. There are actually snowballs coming off of this comet, pieces and chunks. It's a shame it's really a lot better on my screen. The other thing that came out of this comet compositionally, we started seeing evidence for lots and lots of CO2. We've seen this also for ISON. This is a little surprising. We had thought that carbon monoxide was the fundamental molecule in comets. And if you go and look in the astronomy literature, people have studied galaxies and done carbon monoxide maps of the galaxies, and it's usually associated with H1 and H2 regions. So carbon monoxide is CO, just one less oxygen atom, and it's a simpler molecule. So you would naively think that that would be the fundamental cosmogenic molecule in comets, in the galaxy, in the solar system. We're seeing evidence now that it's very possibly, also with a new survey by Subo et al. Using the Carey spacecraft, that it may be CO2 that's actually the fundamental molecule. Nobody has ever really mapped the galaxy or the stars, the heavens, very well in CO2 because we have CO2 in our atmosphere. You can't do it very easily from the ground. But we're seeing hints, and including also from Comet ISON, that maybe we need to go back to the drawing board and we maybe talk to our astrophysical friends about looking for CO2. All right, I need to wind up here because I think it's time. There's lots of other stuff, but I will leave you with a picture of the moon, just because I don't like that, it's really kind of blurry. This is the moon in false color. That's how heavily cratered the moon is. And I want to remind you that that's how heavily cratered the Earth was. Okay, 3.6 to 3.9 billion years ago. This is what we think happened. There was a belt of these are the Kuiper belt objects, and that when Jupiter and Saturn crossed a certain way, they've just blasted them all out of their orbits, and 99% of them are gone out of their orbits. And we think that the Earth and the moon got that. And so there was a rain of asteroids and comets onto our body. On the other hand, everybody's idea of the Earth being a molten ball of lava when it first forms is probably correct. If you do a very simple analysis, the amount of energy it takes to associate, to just bring all the mass of the Earth together, gravitationally, all that energy is 10 times the energy it takes to melt the Earth, to turn it into a lava ball. So the Earth was molten and most likely blew off and got rid of all the volatiles in it, and then it had to freeze. And when it froze, it was a frozen, barren lava ball. And then it wasn't until this event, the one that scarred the moon and also the Earth, and some of the oldest rocks on the Earth are showing some evidence for this now, that may have brought the seeds of life to Earth. And those would have been the organics in water and comets, for example. We still argue exactly over how much of the oceans that comets could have brought, but stay tuned. We still think, many of us think it could have been a good fraction. We're not sure. Could have also been asteroids, could have been water in the Earth. That's an ongoing debate. But I find this exciting to realize that not only are comets good history, they also taught us a little bit about gravity, they taught us about the solar wind, but they may also be the reason why I'm here able to talk to you today. So thank you very much.